Okay, so I think we are ready for the last lecture of this meeting by Rosario Mingione from Parma University. He will speak about recent progresses in nonlinear potential theory. Thank you.
Okay, thank you very much, Luigi, and thanks for the invitation. It's a great pleasure to be here to talk at this memorial conference, and especially to close the whole conference. And you see the alternative title is actually Linearizing Nonlinear Problems, because we will see in a few moments that's really at the core of the Giorgi's theory about regularity, that is giving a nonlinear approach to problems. Okay, before starting, I would like to recall the Giorgi, but I'm not the best person to do this, because actually we interacted essentially zero, because I was too young at the time. But I would like to recall not only the Giorgi, but his legacy in terms of students and in terms of how he influenced nowadays mathematics, not only in the rest of the world, but especially in Italy. This is a list taken by a mathematical genealogy project. You see, he had a lot of students, and these students had, in turn, a lot of many other students. I would like to single out the contributions of Luigi Ambrosio, Gianni Dalmaso, and Giuseppe Buttazzo. You see, they had a lot of students, and so I would like to thank them to keep the thing alive and to keep the level very high. I mean, I think that the whole Italian mathematics should be grateful to all these people, but especially to these three who did so much in terms of raising up students. The list is incomplete. For instance, I do not see Giovanni Bellettini there, and also I think that Sergio Spagnolo should be inside this list, although he formally did not graduate with the Giorgi, I guess. But he worked a lot with the Giorgi, and also he raised up other students and young mathematicians. And this is a picture of the thing that was at that time. You can probably recognize Luigi Ambrosio and Gianni Dalmaso. There is also Emilio Cerbi and Giovanni Bellettini, Vincenzo Maria Tortorelli. And Buttazzo is not there, but I inserted Buttazzo because it was really the case. So why linearizing nonlinear problems? Because essentially, let me point out some basic facts. If you start from this very simple equation, take, let's say, a local solution, then you can get these estimates, these a priori estimates actually for every alpha and also alpha equal to 1. But let's look at these estimates. There are plenty of ways you can get these estimates out, but these estimates are true, and especially also Harnack inequality. That's the standard Harnack inequality. So they follow from basic principles like main value principle or whatever you like. Okay, then you want to extend these inequalities to more general solutions. And then this you can do provided coefficients are continuous for every alpha. This is a classical fact for continuous solutions, but it was a completely high non-trivial fact when coefficients are measurable. When coefficients are measurable, then you go straight on to the so-called de Giorgi-Nash-Moser theory. And in this de Giorgi-Nash-Moser theory, you can prove, and this was actually first pioneered by de Giorgi, you proved the validity of this estimate for a small alpha that depends on the coefficients of the matrix A and especially on the so-called ellipticity ratio. And this is what is main contribution to scalar regularity, and this opened the way to nonlinear methods. Why? Because what de Giorgi did was to introduce a certain set of nonlinear methods that were able to reprove, let's say, the linear results, but also in more general situations. And in fact, as immediately noticed by Stampacchia, Licenska, and Realzam, and many followers, these facts, they keep on being true for nonlinear equations. So the real contributions of de Giorgi is to take the linear results, those that you usually prove using linear methods, but then to introduce and to inject new purely nonlinear methods such that these results can be then extended verbatim to the nonlinear setting. So it's so what he really discovered was the validity of certain general and universal nonlinear principles that were much more underlying the roots of the problems beyond linearity. That's what he did. And essentially, that's what I'm presenting now today. because today I'm presenting some results that are a part of so-called nonlinear potential theory. What is nonlinear potential theory is essentially replicating the results that hold for linear equations, but in nonlinear setting, and especially as far as the shape of the so-called fundamental solution is concerned. And then from this we move to so-called Calderon-Zygmund theory in a natural way. So the plan of the talk is the following one. I start from linear problems, then I describe the nonlinear problems I want to deal with, and then I will show how to get linear results from nonlinear problems, and then we proceed in some sort of nonlinear linearization of nonlinear problems. Nonlinear linearization means that this is not the usual linearization where you freeze the coefficients. This is much more, much more indirect, and really finds its roots in the George's ideas and approaches. In fact, all these things, they rely on some basic estimates developed by the George. Okay, so the part one is about potential estimates. Let me once again start now from this Poisson equation. Now, this you can treat in all the ways you like. A classical way is to get the representation formula via the Green's function. Once you know this formula, you know everything, because essentially you know perfectly how the kernel moves, and then you know how to get properties of the solution in terms of mu. So the main idea is that you want to retrieve as much as possible information of u in terms of the assigned data, which is mu. So this is done via fundamental solution, and with the fundamental solution you can get essentially two estimates. The first one is straightforward. Let me just consider the case n larger than 2 in the first case, and the other one also holds for n equals to 2, and comes from this representation formula, provided you have let's say, a good decay at infinity of the solution. And this comes from differentiation under the sign of integral. Okay, once you know these two pointwise representation formulas that come from the fundamental solution, you know everything. Why? Because then you forget that u or du, they solve an equation, and then you just look at the behavior of this operator, which is perfectly known. This is the so-called Riesz potential. It's a classical operator, and its mapping properties in essentially all kinds of reasonable function spaces, rearrangement and non-rearrangement function spaces are known. And this is a consequence of the fact that you have a fundamental solution, a representation formula, and in a certain sense, everything is okay. This was probably already known to Gauss in a way or in another. And then it propagates over the centuries with the increasing rate of rigor. But essentially, it was clear for a long time. It has been clear for a long time. Okay, from now on, just let me take a break. From now on, let me rewrite the Riesz potential in the following way. This is not cheating. This is just a rewriting of the Riesz potential, because you see, the Riesz potential, when instead of 2 or instead of 1 you put beta, it's on the global on our end, but if you are interested also in local estimates, so you want to be more general, you have to define a properly localized Riesz potential, and this is just another way of writing it. In fact, this is obtained in the following way. You restrict the classical Riesz potential operator to a domain, to a smaller ball, and then you make, let's say, integration by parts or a simple dyadic decomposition on annuli, and then you can introduce the so-called truncated Riesz potential. Okay, once you get the truncated Riesz potential, this is the right object that from now on we call Riesz potential. Okay. Now, one of the main aims of this talk is to show that although these representation formulas, let's say these two inequalities, they seem to be completely linked to the linear nature of the problem, they are not. And this already reminds what De Giorgi did, because De Giorgi proved essentially the same linear estimates for nonlinear problems. And now we want to do the same in the setting of nonlinear potential theory. So in particular, I want to consider, let's say, nonlinear Poisson equation in the sense that I switch from linear to nonlinear equations that are non-degenerate, and the non-degeneracy is described saying that the eigenvalues of the first variation of the vector field are bounded from above and below. And then eventually we also want to go to degenerate equations, for instance, of P-Laplacian type. The P-Laplacian type is a pervasive operator nowadays starting from the 60s. It comes just, for instance, from the minimization of this simple energy. If you take this functional and then you consider the so-called Euler-Lagrange equation, you come up essentially with this equation. Okay, so, but let me stress that the point here is not treating degenerate equations. The real point is the jump from linear to nonlinear theory. So this is the real point. So essentially, the conceptual novelty of all these things already happens at the first stage in the non-degenerate case. Okay. In particular, when switching then to degenerate equations, I will consider more general equations with this kind of rate of degeneracy. And these assumptions are classical since Lagrangian and Dury-Alzheimer and essentially are introduced everywhere to mimic the properties of the P-Laplacian operator. Okay, and then you immediately see that if you want to get for nonlinear equations estimates of the type that we saw for the Poisson equation, but P is different than 2, then you cannot get these estimates. You cannot get these estimates because they simply do not respect the scaling of the equation. If you consider this equation, you see that this term scales like P minus 1, this term scales like 1. This means that if you multiply a solution by a constant, this is a solution of a similar equation, but the constant doesn't scale linearly. Scales with a deficit scaling of P minus 1. So for this reason, it is classical to introduce these so-called Wolff potentials that, although being called Wolff potentials, they have been first introduced by having and Mazziai in a fundamental paper from '71. So Wolff potentials are nothing but the classical Riesz potentials incorporating the deficit scaling of the equation, 1 over P minus 1. So, and when you make this, then you try to guess that the same estimates are true, replacing Riesz potentials by Wolff potentials. They intervene, they are ubiquitous in linear potential theory. They essentially play the role of Riesz potentials when you want to characterize fine properties of Sobolev functions and P is different than 2. They reduce to Riesz potentials when P is different than 2, when P is equal to 2. And essentially, what you're doing is nothing but making them nonlinear by introducing this deficit scaling exponent of the equation. So the first result in this direction is a beautiful result of Kilpelangen and Mali, who essentially proved the following, that exactly as in the case of the Poisson equation, you can pointwise bound U by the Wolff potential. And this Wolff potential is this one. You see, when P is equal to 2, this is n minus 2, this is 1, and then you get the Riesz potential. You may wonder that there's an additional term, but this additional term is not very important. Why? Because with R, capital R fixed, this is a constant, but it must be there. Why? Because when capital R goes to 0, then this is an integral, and it goes to 0 provided it's finite, and then you get U less than or equal than itself. Otherwise, you would get 0. But if the solution decays properly, then you can send capital R to plus infinity. This term disappears because it has an average involved, and then you get U less than or equal than the Wolff potential with a global estimate. So this is essentially a linear type estimate that is now found to be working for a nonlinear equation, which is which is allowed to be degenerate when P is different than 2. And in fact, the proof of Kilpelangen and Mali rests also on the George's truncation and iteration method. Okay, this is as far as the nonlinear analog of the first estimate is considered, and you see that for when P is equal to 2, we go back to the Riesz potential. Okay, what is the advantage of this estimate is exactly that it allows you to do the same things that are true, that you usually do via the representation formula with a fundamental solution in the nonlinear setting. Because at this stage, if you want to, for instance, to retrieve the best possible integrability results for U in terms of those of mu, you just forget that U is a solution, and then you just apply this one, which is a sharp estimate because in the paper of Kilpelangen and Mali, there's also lower bound provided U and mu are positive. So you cannot get better than this. For instance, the mapping properties of the Wolff potentials are known, and since they are known, you just forget U and the equation, and then you just check where the Wolff potential is mapping the datum mu. And this is known because it rests on this following fundamental estimate, which is due to Mazziai and Avin from '72. Actually, for P larger than 2 at least, but for actually P larger than 2 minus 1 over n, I guess, this is a double-sided estimate. And this is called having a Mazziai potential. Is nothing but a nonlinear iteration of Riesz potentials. Since the behavior of the Riesz potential is known, then the behavior of the having Mazziai potential is known, and in turn, due to this inequality, the behavior of Wolff potentials is known. So this closes the issue, this beautiful paper of Kilpelangen and Mali, and is essentially is essentially it's essentially closing the issue. Okay, what about the second estimate? And the validity of the gradient estimate has been remained an open issue for a long time since the paper of Kilpelangen and Mali. Why it has been debated? Because first of all, this estimate is believed to reproduce the behavior of the fundamental solution. Kilpelangen and Mali have a double-sided estimate because essentially they tell you that the solution is trapped between two Wolff potentials exactly as the fundamental solution should be via convolution. This is obviously false for the gradient because there's no maximum principle. And moreover, also from the technical viewpoint, if you want to get a gradient estimate, what you usually do is to differentiate the equation and then to discover that the gradient is a solution of a different equation. But here there's nothing to differentiate because on the right-hand side you have a measure, and Calder-Zygmunt theory fails when you have L1 and even worse a measure. So this was debated. Nevertheless, I was able to prove it first for the case P equals to 2, only many years later. Actually, the paper was written in 2008, and then it appeared later for backlog issues. But this estimate tells you exactly that the same estimate works for the gradient. So for the gradient, you can have this estimate, which is exactly the same one that you get for the Poisson equation. In particular, if the solution decays properly, and decays properly means that it usually satisfies the same decay properties of the fundamental solution of the problem. Let's say, take P Laplacian of U, or take Laplacian of U equals to a Dirac, write the fundamental solution, get the decay, and prescribe this decay in your solution, which is at this stage natural, because the fundamental solution is, in a sense, the worst possible solution. Then you get the usual estimates on the whole Rn. So this is, let's say, a complete linearization of the gradient theory. And once you have this result, you can then restart the whole program. If you want to get gradient estimates, you then forget the equation, you can forget whatever, and then you just use this estimate and you check where the gradient is. Of course, this estimate fails to be double-sided because the gradient can be perfectly flat for its own reasons, and this is a consequence of the lack of the maximum principle for the gradient. Okay, so for P equals to 2, the story is closed. And okay, what do you usually do for the case P larger than 2? And then the usual ansatz is to use Wolff potentials. Wolff potentials, they are bound to replace Riesz potentials whenever the equation is degenerate, and so the orthodoxy of the classical nonlinear potential theory, as for instance is described in the paper by Kilpeläinen, Heinonen, and Martio, which is a classical monograph in this theory, is that whenever P is different than 2, you replace the Riesz potential by the Wolff potential. And so the first guess is that you want to get a gradient estimate via Wolff potentials. And in fact, this we were able to prove with Frank Dussart a bit later. And with Frank Dussart, we proved this estimate, that you can once again pointwise bound the gradient via the Wolff potential. And the Wolff potential this time is this one. When P is equal to 2, then it's once again I1, the usual Riesz potential that you expect to find when P is equal to 2. So once again, you can rerun the same program, and that's apparently the end of the story. This was the solution of the problem posed by after the paper of Kilpeläinen and Mali. But then there's a twist now. Because essentially when you find estimates for solutions of equations, you first have to guess the shape of the a priori estimates you want to have. And the shape of the a priori estimates is directly suggested by the shape of the equation. So the shape of the equation is the following one. Take this equation as a model equation, and then just formally decouple it in the following way. Now just concentrate yourself on the second line. How do you usually solve this equation? There are many ways. For instance, you can look at the paper by David Price. Then there's a paper by Bourgain and Brezis. There's a paper by Da Corogna, Fusco, and Tartare. There are old papers in the school of St. Petersburg. There's a well-known Bogowski's theorem that essentially they all tell you the same thing, that you can solve this equation by representing V via the Riesz potential of mu, because the Riesz potential is an integration. If you apply the Riesz potential to both sides, being I1 an integration, it cancels the divergence, and then you stay up with the following estimate. So the equation is telling you something different. The equation is telling you that you are not bounding the gradient via the Wolff potential, but you're bounding the gradient via Riesz potential, which is completely unorthodox from the point of view of the Riesz of the standard nonlinear potential theory. And of course, this is completely unorthodox because the standard nonlinear potential theory tells you that you have to use Wolff potentials, but the equation is telling you something different. Of course, you might like to apply this method. You can solve this equation, but you're never sure that you get the solution in this form. So the equation is telling you that this estimate should hold true. And in fact, this estimate is true. And in fact, we were able to prove this estimate, which we safely conjectured to be completely sharp, because that's what the equation is telling you. This equation is telling you the surprising fact that no matter the equation is degenerate and nonlinear, you're bounding the pointwise the gradient via the Riesz potential, exactly as in the Poisson equation. And this can be even rewritten in a more suggestive way, which is the following way, because A of du controls by coercivity du to the p minus 1, and this is what you get essentially in the equation. Apparently, an estimate that is suggested to you by applying I1 to both sides. If you're applying I1 to both sides, I1 cancels the divergence, and then you get what is under the sign of divergence bounded by I1 on mu. Okay, consequence of this estimate, it's essentially a new principle in nonlinear potential theory, because although the equations are nonlinear and degenerate, you can control them with linear potentials. The less philosophical implication is the fact that now you can once again rewrite the same program, and this estimate in a certain sense unifies the gradient theory of the P Laplacian type equations. Because essentially you get all the same properties. You can rerun the same program. You know how the Riesz potential is behaving, and whatever you want to know about the gradient, then this estimate is telling you, because it fully reproduces now literally the behavior of the convolution via the fundamental solution. Consequences just for the model equations, it's a complete unification of the previous theories got by completely different methods. Because you see, this estimate works for solutions to measure data problems. They are not energy solutions. So they they require different treatment from the case that you get for energy solutions. For instance, for this equation, the well-known and classical results by Ibanez and Di Benedetto Manfredi now they follow. And I'm talking about higher integrability of the gradient. Then the classical theorems in the classical paper by Adams on Duke are straight away extended to the P Laplacian case. Then the classical theory of Boccado and Galloway for this model case can be reproduced. Of course, we are relying on the ideas of all these people. It's essentially, the proof of this result is highly, let's say, non-trivial. It takes 40 pages of writing. But then at the end, you get a unification of all these classical theories. There are classical estimates by Talenti and endless series of, let's say, refinements by a number of followers. And they immediately follow by this estimate now. And this is a very general principle. Yeah.
What is wrong with taking the Riesz transform of the equation?
Yeah. Try. Because you are taking the Riesz transform of something which is in divergence form, but I will show you that it's differentiable. And then you have to differentiate once again. So the divergence, it's equal to a measure. And it's not completely clear in the way you can do it. Because otherwise you would immediately get also the Giorgi's theory with this method. That's exactly. Because apply this fact to the Giorgi's setting, and then you get the Giorgi's. So there could be a problem there. Probably this was taught in the 30s by Morey. Okay. And okay. And then this is a very general principle. This is a very general principle. This is a very general principle because Baroni proved that this extends to all kinds of reasonable elliptic operators, no matter the polynomial growth you have. No matter the polynomial growth you have, and this is not a completely clear fact. It's not a completely clear fact. And estimates in the vectorial case. And this is a quite, this was open already in the case of Kilpelangen and Mali, so it was not known a pointwise estimate of U in terms of Wolff potentials. And then this was proved by us, by once again Kuusi and myself, and Tuomo Kuusi is a very brilliant guy working in Helsinki at the moment. And you can pointwise bound U via the Wolff potentials, but being even more precise. Of course, everything in the scalar case also holds now for equations. And I would like to point out that in the scalar case, you cannot get all these results for general equations. Because in the vectorial case, when you do consider systems, already when you have a right-hand side, systems show up with singularities. And therefore, you need the precise structure. And one of these instances where you can prove everywhere regularity is the Uhlenbeck result. Is this Uhlenbeck type structure. And then you can prove this estimate, and this also settles this issue of the validity of Kilpelangen and Mali's results in the vectorial case. Moreover, the gradient estimate is of similar type as before, but with a much more sophisticated way, because now you can already bound oscillations. You can immediately bound oscillations. And when you bound oscillations, then this tells you that the potential is not only bounding the U pointwise, but it's also bounding the oscillations of the gradient. And therefore, this is a premise to get continuity from potentials, as we are going to see in the next part of the talk. This is a very, very delicate. This is a very, very delicate issue. The proof is very delicate. It takes, including the previous parts of the theory, you have to rearrange. It takes almost 80 pages of heavy computations. And the reward is rather high, because then once again you get the previous results plus the ones that were open. For instance, there are classical results for this model case. There are classical results by Dolzmann, Ungenbüller, and Müller that you can now prove straight away, but just for this model case. Then Dolzmann, Ungenbüller, and Müller, they also have measurable coefficients and blah, blah. So I'm just considering a unification on the model case, on the P-Laplacian system with the measure. Then the whole classical measure data theory of Boccado and Galloway was not extended to the vectorial case. Now can be extended immediately, because essentially you have an estimate via Riesz potentials that gives you everything. So the whole theory can be raised up to the vectorial case. And also the Talentis theory and the Talentis estimates for via rearrangements in function spaces can be now extended verbatim to the case of the system. Because essentially the method is very general, and once you have a pointwise estimate, then you can go on. Okay, this was a very long-standing issue raised by the paper of Kilpelangen and Mali, that there were some attempts to build the theory in the vectorial case, but now with this estimate you can get essentially all the rest. And in particular, we also observe that we are able to reproduce some very, very classical potential theoretical facts. The standard and classical potential theory is actually about the study of the fine properties of solutions of Poisson equations and harmonic functions. And one of these classical facts is that you want to study the fine properties of solutions and the fine behavior that essentially means that you can study where there are no local blow-ups of the solutions, where are too many wild oscillations, and then you want to exclude them by catching all Lebesgue points. And then we prove the nonlinear degenerate analogues of some classical facts proved in classical potential theory by the school of Choquet, then Brelot, and in the 30s. For instance, we proved that if at one point you get that the Wolf potential is bounded, then this is essentially a Lebesgue point of view. There exists the fine representative at that point. And in turn, if I1 is bounded, then the gradient admits the fine representative at that point. And so this is just another example of the results that you can get using these kinds of estimates. Okay, let me look back at these estimates. Here you see du minus the average. Dimensionally speaking, this is the oscillation. And this estimate starts telling you one thing, that you can pointwise control an oscillation using two things. The mean of the oscillations plus the potential. Now, you know that when you can control a pointwise value by a mean, then by iteration, this means that the solution must be regular. So now the whole game, this means that the whole game is left to the potential, which is on the other end assigned. So this means that, in other words, the potential should control the oscillations of the gradient. And this is the content of the next section, oscillations. How we do control the oscillations of the gradient via potentials. A second theorem that is from this paper tells you that if you have a solution of this equation, and if this guy is locally bounded, then du is locally bounded. This is a triviality because follows from the pointwise estimate. This is a completely trivial fact. As a corollary, this solves a very long-standing conjecture of Uraltseva. A conjecture of Uraltseva stated that, let's say, a very classical open problem of the theory was to find the sharp condition on the right-hand side, allowing you that the gradient is locally bounded. In other words, you're looking for local Lipschitz continuity of solutions. Uraltseva predicted, as I was referred by a number of people, that this condition should be independent of P, probably because Uraltseva herself made this heuristic argument of applying I1 formally, let's say. And in fact, this condition is already a condition which is P independent, because this is P independent. You don't see here P anywhere. So in a certain sense, this is an indirect condition, because no function space or no specific condition is prescribed, but just the behavior of the potential. So this is okay. And now let me see a few corollaries of this theorem. So let me apply this theorem to special cases. Another theorem we have that actually reinforces the previous one is the following one. You remember that this is an integral. So if it's pointwise, if it's bounded at one, if it's finite at one point, then when capital R goes to 0, it goes to 0 by the absolute continuity of the integral. Now we prescribe that it goes to, in particular, it goes to 0 at every point, provided it is bounded at every point. Now we reinforce this condition, and we prescribe that it goes to 0 uniformly with respect to x. This implies that the gradient from L infinity jumps to C0. So essentially, the good decay of the Riesz potential reinforces the good decay of the measuring side that forces the continuity in the right dimensional setting. A few consequences. Let me get you one consequence. This is a classical theorem of Stein. A classical theorem of Stein tells you that the borderline limiting case of Sobolev embedding theorem, it's not Ln, that it cannot be, that only ensures that V is VMO, but it's Ln1. So what is Ln1? This is a Lorentz space which is slightly smaller than Ln, but which is still larger than all Lp for P larger than N. And another way, these are interpolation spaces, and another way which is essentially equivalent to this theorem is the following one. If you get Laplacian equals to mu, then you get that if mu is in L, if it's in this space, then the gradient is continuous. The gradient is continuous. And what are these spaces? Examples of functions that are in these spaces. When teaches function spaces should always start with examples, because function spaces are, let's say, something you introduce because you have a particular function in mind. Otherwise, it's likely that you're doing some dangerous abstract nonsense. But Lorentz spaces are important because, in fact, they encode the logs. Let me show you an example of a Lorentz function. So essentially, what is after powers? Powers are described by LPs, spaces, and the next thing that you get after powers are logs, and Lorentz spaces describe logs. And essentially, this theorem of Stein is the borderline theorem of Sobolev embedding theorem. When epsilon goes to 0, you would formally stop to ln, but ln is not the right one. You have to stop to ln1. You have to stop a bit before, because otherwise there could be a log explosion. In fact, why? Because then divising ln means that the B is BMO. BMO is close to BMO. What is the difference between BMO and L infinity? It's a log. The log that you are missing from the solution, you have to put in the space, and in fact, the log is the Lorentz space. It's a complete shift of the game. Okay. And in fact, you see the logs immediately. So the log that you want to get rid of, you get rid for the solution, you have to put on the datum. It's just shifting the things. Okay, but then an almost trivial fact is that when mu belongs to ln1, then this happens. So the criterion for the gradient continuity is satisfied, and what you come up with is a neat nonlinear theorem of Stein. The Stein theorem is the following one. This consequence is the following one. This is what we call nonlinear Stein's theorem. And this is essentially a more precise answer, or just a rearrangement functional space, theoretical functional space answer to the classical conjecture of Uraltseva, because the right-hand side, this condition is obviously P-independent. And this is one example. Then you can check from time to time when the condition is satisfied, and then to find other conditions. For instance, there are density conditions, Maury type conditions, but this is let's say, a nice condition that, let's say, extends naturally the classical fact of Stein. And more consequences you can find in a nice recent paper of Alberico, Cianchi, Bordone, and it also works for the vectorial case, because what I forgot to mention is that all these continuity results, they keep on being true for the vectorial case, but of course when you do consider the P-Laplacian system and not any general system. And now we have treated conditions ensuring you that the gradient is continuous, and now we look for more precise conditions and more precise moduli of continuity. And now the next and second last section is to show you that now we have seen two estimates, one estimate for u, one estimate for the gradient, and now we shall see that these estimates are actually two special cases of a more general family of estimates that we are going to call universal potential estimates. Okay, the universal potential estimates are suggested once again by the analysis of the Poisson equation via the fundamental solution. Via the fundamental solution, you can get this trivial, almost trivial inequality. You can trade a bit of integrability with Hilbert continuity. You can check the homogeneity of this. As a consequence of this, you get the following representation formula. The following representation formula tells you that you can pointwise bound u x minus ui by this sum, and then you get this. And this opens the way to these universal potential estimates. But first, let me introduce a concept that was introduced by Devore and Sharpley. Devore and Sharpley essentially introduced what they call Calderon spaces, although the techniques they use are really coming from Campanato, from the 60s. Okay, you say that, okay, these are fractional type spaces. You know, fractional spaces are nowadays very popular, but there are plenty of ways you can describe the concept of fractional differentiability. Gallardo norms, Minkowski spaces, Biesov. This is another way which is close to that. Okay, you are prescribing that the oscillations of the solutions are like Hilbert continuous, but with a potential blow-up that it's related to LQ. So when Q is infinity, you get the standard Hilbert continuity. Otherwise, you are prescribing locally the potential blow-up of these oscillations. These are close to W alpha Q spaces, and in fact are slightly larger than them. But they are very close, tilting a bit Q or alpha, as usual. And let me point out that this condition can be, since this is itself a metric, it's very much related to a condition which is very popular nowadays of describing Sobolev spaces in general metric spaces. In fact, the basic observation is that you can always use a fractional type operator, fractional maximal type operator for mu. This is the basic observation of Devore and Sharpley, and years later I was also had the idea of extending and using similar definitions to define Sobolev spaces or metric measure spaces. Okay, after all this, we come up with the fact that this is just a way to say that this is a derivative of a fractional derivative of V. And then the universal potential estimate is the following one. The universal potential estimate tells you that you can pointwise ux minus uy getting the Hilbert continuity by a family of interpolating Wolff potentials. So these are telling you that you are not only controlling the pointwise bounds, the pointwise value of the solutions via the potentials, but also the oscillations. The more you are requiring on the modulus of continuity of the solution, the more you are requiring on the potential. And this, according to this terminology, tells you that you are pointwise bounding the fractional derivatives by properly Wolff potentials. When alpha is equal to 0, this is Kilpelangen and Malin. When alpha is equal to 1, this is the estimate that Frank Duzar and myself developed for the Wolff potentials. This estimate is, of course, so this estimate tells you that both the Kilpelangen and Malin estimate and the Duzar and myself estimates are two particular cases of a more general family of estimates. So in particular, if you want to know conditions for which this is locally Hilbert continuous or this is in a fractional Sobolev space, you just once again look at the behavior of the Wolff potentials. Of course, if alpha is getting larger, you are requiring more, and making this guy bounded or locally in some spaces becomes more difficult and gives you different conditions. But the philosophy is rather simple. This estimate is sharp for alpha is equal to 0 because it's Kilpelangen and Malin, but fails to be sharp by very little piece because it doesn't give you Riesz potentials and it cannot. And in fact, this is the content essentially of the estimate. And when mu is equal to 0, this reduces to the classical estimate. And when P is equal to 2, this is the usual estimate that you get for the Poisson equation. So this is completely sharp. But now works for any general equation. So the new idea of this paper is essentially to observe that you can always, and you can also embed the Giorgi's theory into this, because you can also allow for small alpha measurable coefficients, but just for small alpha. So you can describe you can describe, let's say, a nonlinear potential theoretical version of the Giorgi's theory with Wolff potentials. But then you should look at the paper. Okay, we also have an estimate which is sharp when alpha goes to 1. Because when alpha goes to 1, now we approach the estimate I have with Tuomo Cusi. Of course, this fails to be true when alpha goes to 0, because when alpha goes to 0, this would give you a better estimate, an estimate which is better than Kilpelangen and Malin's. But this fails to be true with the right blow-up with respect to alpha. How you get this estimate? You get this estimate by introducing and using fractional operator and sharp fractional operators. when beta is equal to 0, you know this is the classical Hardy-Littlewood operator, otherwise it's the fractional maximal operator. And when beta is equal to 0, this is the classical Pfefferman and Stein sharp operator, otherwise it is what it is. It's called fractional sharp maximal operator. What we prove is a general estimate that tells you that you can pointwise bound both the fractional sharp operator and the pointwise fractional operator by Riesz potentials. And you know this is completely sharp because there's no alpha here. There's no alpha involved here. There's no blow-up. Then when you try to convert this into a pointwise estimate for U, this is stable when alpha goes to 1, and this is unstable when alpha goes to 0. And this is done via this general inequality that holds for any function. Sorry, here there should be a V, not an F. And this is essentially the maximal estimate I was talking about. We also have, let's say, an estimate that goes beyond Lipschitz continuity. You know that if you take the P-Laplacian estimate and the right-hand side is equal to 0, there's a classical theorem of Uyaltseva that states that the gradient is Hilbert continuous for a certain exponent. So you would expect that you can raise up this theory when the right-hand side is not 0 via Wolff potentials, and you can still do as long as you do not catch the maximal regularity. So you fix the maximal regularity exponent of the P-Laplacian operator, and then you end up with this estimate that holds as long as it can. Okay, final thing, and now I treated estimates via Riesz potentials, and these are fractional operators. The limiting case of fractional operators are singular operators, and this cannot be any longer treated by means of size inequality, but unit cancellations. And now we go into a very more specific way, which is what can you say about Calderon-Zygmunt theory for nonlinear problems in the limiting cases? Okay, and now let me recall you the definition of fractional Sobolev spaces. The definition of fractional Sobolev spaces is the following one. You prescribe that V is in WS gamma by saying that the oscillations of V have to be small enough to compensate the blow-up of this kernel, which deteriorates as gamma goes to 1 and gets better and better when gamma goes to 0, and everything is measured in the L gamma norm. By scaling, this should be thought as the norm of an alpha derivative whenever it could be expressed pointwise. But the main fact of these spaces is that fractional derivatives are non-local objects. But if they would be, this would play the role of this. And they do come along with their own Sobolev embedding that reduces to the usual Sobolev embedding when S is equal to 1. Okay. And for measure data problems, you cannot have then the right-hand side is in W11. This is the classical failure of Calderon-Zygmunt theory when the right-hand side is L1. Why? Because otherwise you will get this and the fundamental solution is just not there. The fundamental solution misses from being there just by a log because it's in a Marcinkiewicz space. So we have the following fact that if you get P Laplacian of U, or just let me take P equal to 2, a nonlinear equation, that if the right-hand side belongs to LQ, then you have, and Q is larger than 1, then you have second derivatives in LQ, but when Q goes to 1, you lose everything, and this is a clear gap in the theory. The theory of measure data problems, as it was when I was writing the paper I'm going to talk about, was just a gradient integrability theory. Otherwise, you just lose everything about differentiability. So this gap was filled by myself in an old paper that tells you that if the gradient cannot be in W11, then it's in every fractional space before the forbidden one. So you are as good as you can before you cannot be. And this is a very delicate thing that uses a sort of nonlinear analog of local Little pellet decomposition, inspired by the fact that you have a characterization of fractional spaces via atoms.
And the idea in the classical setting that it's used to treat for linear problems is that this atomic decomposition uses atoms that are harmonic functions. Here you use atoms that are solutions to nonlinear problems, but that are homogeneous. And then you make a cover that reminds you this little Pelly decomposition. This is for p equals to 2. What about, and this comes along with a local type, inequality, with a local inequality which is of Cacciopoli type. Let's say higher derivatives are controlled by lower derivatives, plus the right-hand side. What about the case p different than 2? And then you just look at this condition. You play with these parameters. Now you fix gamma is equal to p minus 1, and then you can get the best possible S. And this comes along that this is where the fundamental solution is. So if you look at the fundamental solution, this is the best you can get, and this is the prediction. And in fact, this is what you prove. This is sharp for p equals to 2, as seen before. And it cannot be better than this one, because otherwise you would use Sobolev embedding theorem, and you would get that the gradient is in the forbidden space. It's only Marcinkiewicz. And on the other hand, this gives you back Bocardo and Galois theory by embedding, because now you do a step up. It's the classical fact. If you get higher possible regularity, then by embedding you get higher integrability. But now let me point out that there's something we do not like when p is different than 2. Why? Because also when epsilon would be 0, you get a fractional exponent, which is natural because it's the scaling of the equation. Because the right-hand side scales as 1, the left-hand side has k is like p minus 1. The first index measures the oscillations, and it cannot be nothing but 1 over p minus 1. This is the equation which is telling you this. But on the other hand, we have seen that if you approach to an intrinsic viewpoint, then you go to, let's say, to the maximal regularity. You recover regularity. And this is the content of a very recent preprint that we have with Aveling and Cusi that tells you the following completely linearization phenomenon. Divergence A of du, just cancel the divergence, and it's in W sigma for every sigma less than 1. So the idea is that when you look at the gradient, you lose differentiability. But when you look at the so-called stress or flux tensor, let's say the whole equation that incorporates the degeneracy, then you recover the full differentiability, or the almost full, because actually there's a way to say that sigma can be gone to 1, but then you should not use these spaces by other spaces, but this is too technical. But in the limiting case, you can get the same thing. And this is a very striking fact, because this is a completely nonlinear approach to the classical Calderon-Zygmund theory, in the sense that you are not using fractional integrals anymore or cancellations, but you are going really to the core. And in particular, you see that this is exactly the same thing that you get via fundamental solution by Calderon-Zygmund theory. You just cancel the divergence and you gain one derivative. This is the classical Calderon-Zygmund theory. And this gives you a complete linearization phenomenon and this I would consider really the endpoint regularity for the measure data problems, because now you go really to the flux and you consider the equation as it were not elliptic. In some sense, you use ellipticity to build something that can be done as a linear equation. And this takes 50 pages of delicate computations. But then at the end, the statement is very neat, because it's exactly what you would expect by formal analysis, by dimensional analysis. And in particular, this comes along with an a priori estimate. The a priori estimate is first derivative, almost first derivative, less than or equal than itself, plus the right-hand side. And this should remind you this other estimate. This is the counterpart of the potential estimate. The potential estimate is a potential estimate for du, and it's via Riesz potentials. When you step up from the gradient to the almost maximal regularity, that's the almost second derivative, you step up from fractional integrals to singular integrals, which are hidden, in fact, in this estimate. So these two estimates should be considered as dual to each other. This is the intermediate pointwise regularity, and this is the maximal regularity in the Calderon-Zygmund type. And finally, I would like to close with even more interesting fact, which is, let's say, a nonlinear analog of what is in complex analysis called uniformization of singularities. So what you do to get holomorphic or harmonic functions from bad functions in complex analysis, you raise them to a power which is higher than 1. Think of modulus of x, which is non-differentiable. Then you raise to the square, and then it becomes differentiable. If you raise to a higher power, then you increase differentiability, but you're losing integrability. And this is the full phenomenon that we have here. Consider this fact here, and consider gamma that stands from p minus 2 to 0. When you get p minus 2, if you think of the p Laplacian, this is the flux of the p Laplacian. When gamma is equal to 0, you get just the gradient. And then you give different rates. You increase. If you increase gamma, then you get better differentiability and worse integrability. But the product is always the same because the product regulates then the endpoint regularity of the fundamental solution. In particular, this catches up the result from the new paper with Daveling and Cusi and the old result of the paper on Agnelli di Pisa, where in fact this result was originally conjectured. Because at that time we didn't have all this insight in these linearization processes, and I only knew how to differentiate the gradient, and we didn't know how to manage the whole flux. And now using these ideas and combining with them with other observations, we can have a full picture, and in some sense we can give a full picture of the theory of quasi-linear equation that brings the whole theory to the linear theory back. And this was conjectured there. And further directions, what about parabolic theory? We have a complete parabolic theory in the scalar case, and we are working on the vectorial case. But this is very much more technical, and this involves the use of intrinsic geometries of Di Benedetto combined in the setting of nonlinear potential theory. And we have also a similar approach that works for fully nonlinear, and when you work this for fully nonlinear, which is actually a bit easier because the equations are not degenerate, then we are able to provide the limiting borderline cases of the classical results of Caffarelli and Teudinger, exactly as we did here for cases. And then we also have a theory that works for you in the case of fractional operators. And this is a recent result with, this is with Tuomo Cusi, this is with Totti Daskalopoulos and Tuomo Cusi, this is with Yannick Cyr and Tuomo Cusi. And actually, this is the end of the talk, and I would like to go back on the pictures because at the beginning, I showed you, let's say, the school found by De Giorgi with people like Luigi, Gianni, Giuseppe, and other people. Then I should go beyond. And I should tell you that also De Giorgi has predecessors, and these are, let's say, the scientific and cultural predecessors. And I would like to point out the leading figure of Tonelli, that was here at Scuola Normale. Okay, I should also put Dini before, but then it's not the case to go in other centuries. But staying in these centuries, the calculus of variations was really launched by Tonelli, because Tonelli was working on the, let's say, a calculus of variations, a one-dimensional calculus of variations, but from a nonlinear viewpoint. And this was, let's say, the nonlinear functional analysis, and it was very pioneering. Because at that time, they were studying linear functional analysis. While if you study those kinds of functionals, you are doing functional analysis in the 20s, but it's nonlinear. So there's a big difference. And from Tonelli, and during all those years, while Tonelli was a bit declining, then Cacciopoli was standing up in Napoli. And then we go back to Scuola Normale with Ennio De Giorgi, who took the heritage of the last of the late Cacciopoli, that was probably not able to, for personal problems, to technically develop his ideas. And this is the point where De Giorgi comes into the play. He takes this very I would say, very brilliant and visionary ideas, but yet technically major ideas of the Caccioppoli and start developing. And so I think this is a good point to end my talk, and thanks for the attention.
So thank you very much. Questions, comments?
How are your ideas or techniques can be extended to the case of more general norms instead of the Euclidean norms? Suppose that you have a or maybe uniformly convex but not quadratic norms of the gradient.
For the gradient, so what do you exactly mean? You take a different equation, so you can study in different function spaces. You take a different structure in the equation.
No, it's the same structure, divergence.
So the P-Laplacian operator, but in different spaces, or?
No, but the norm is not the Euclidean one.
It depends on the norm. It depends on the norm, because if you then, for instance, if you look at these pointwise estimates, if the norm has some discontinuities or other things like that, then this means that you take the new equation and you transform it into another equation which is in the Euclidean setting, but probably with discontinuous coefficients. So it's not clear at this stage. So you should really go from case to case.
Thank you.
More questions? Comments? Okay, so if not, let's thank, sorry.
Take this opportunity to thank the organizers for this wonderful conference of high scientific interest, and for bringing us together to celebrate not just De Giorgi, but also the Scuola Normale.
And many thanks again to all speakers and also to all participants.